Hello students, in today's lecture we will be solving the example number 2 from NCERT textbook. So the example stated over here is having few subparts. We'll start with subpart A. This question, as we have seen in the example number 1. In example number 1, what we have seen the drift velocity which we got as 1.1 millimeter per second. Then we compared this drift speed with the speed of our copper atom at room temperature which was equals to 2 into 10 to the power 2 meter second, and then the same VD was compared with the velocity of EM wave which is equals to the speed of light, that is 3 into 10 to the power 8 meter per second. Here what we have seen is that the drift velocity is comparatively very smaller with respect to the speed of copper atoms vibration at room temperature as well as the speed of electromagnetic waves. So with respect to this particular data provided, we got a question here as a subpart 1 of question number 2, which is the electron drift speed is estimated to be only few millimeter per second. Yes, we have seen this in example 1. For currents in the range of few amperes. Current provided in the previous question was 1.5 amperes. How then is current established almost the instant a circuit is closed? So here the question is, as soon as we switch on a tube light, a fan or anything, it starts to light up. Like how can this instantly the current can pass from one point to the another point? Why the current is having such a higher speed if the drift is so less? So let's try to find the solution. Electric field is established throughout the circuit almost instantly with the speed of light, causing at every point a local electron drift. Establishment of current does not have to wait for electrons from one end of the conductor traveling to the other end. However, it does take a little while for the current to reach its steady value. Okay, now it's time for us to understand this question. What exactly the solution is stating that if we consider this particular wire, okay, in this wire at many subpoints we are having electrons, okay, electron 1, electron 2, electron 3, electron 4, electron 5, electron 6. I'm just naming it. There will be many more electrons. I'm just going with 1, 2, 3, 4. So now we are having these many electrons. Now I switched on the circuit, and there is instantly a bulb at this end started to lit up. Okay, it started to lit up. How is that happening? There is this electric field which is generated against, like not against, but in the opposite direction of motion of the electron. There is a electric field generated, E generated like this, okay, and electrons are trying to drift in this direction, okay. Electrons are trying to in the opposite direction, trying to drift in the opposite direction, and E here is in the from left to right, okay. Now as soon as we switched on, this electric field is established from this end to this end. Electric field is established from this end to this end without any delay, with the speed of light, okay. E establish with the speed of light. So this speed, or this E, what it did is I'll just make the diagram once again, a little clear diagram so that we can understand properly. Okay. These are electrons and E is established. Due to this E, these electrons will locally drift a little. Locally implies at that point itself. At every point, every electron will start drifting. Okay. Electron present over here will drift. Electron present over here, here. Everywhere these will drift, a small drift. This multiple small drift will cause a current in the bulb which will light up the bulb. Now, for all the electrons to drift and move to this direction, it will take a little time. So, initially, the current which is flowing through this circuit will be unsteady current. So, after some time, after a minute or two, this unsteady current will convert into the steady current because every electron will be drifted and everything will be uniform. That is what the solution is trying to tell, and that is how instantly, as soon as we switch on anything, any electrical appliance in our home, it starts working. Now we'll move on to the subpart 2, that is subpart B. The electron shift drift arises due to force experienced by electron in the electric field inside the conductor. But force should cause acceleration. Why do then the electron acquire a steady average drift speed? See, we have force equals to ma, mass into acceleration. So basically force, whatever force we are applying to anything, it results in acceleration. Then the force applied by the electric field causes Vd, which is uniform. Why is this happening? Okay, that is the question. Let's understand the solution. For free electrons does accelerate, increasing its drift velocity or speed until it collides with a positive ion of the metal. It loses its drift speed after collision but starts to accelerate and increase its drift speed again, only to suffer a collision again, and so on. On the average, therefore, electrons acquire only a drift speed. So basically what we are having many electrons, and these electrons start accelerating when we are applying a force on it. After acceleration, they catch up the speed. Their speed increases. When their speed increases, the probability of them colliding increases. These electrons, when collides with a positive charge of the atom, they lose all their energy to this positive charge and comes to a lower speed or lesser speed. Again, the same force is applied on these electrons, making them to like vibrate more faster or move more faster or drift more faster. This again and again happens, and so like every time these electrons tend to get more faster, more higher drift speed, they collide with a positive charge and lose their energy, lose their velocity. So at the end, when we see the average of all the electrons, because in a system we have read in the kinetic theory, we cannot take one particular atom or electron. We have to consider the system of electrons or the system of atoms. So for a system, we have to average it out. So when we average out the drift velocity for this system of electron, it comes out to be an average which is just steady. Like it's neither increasing nor decreasing because all the effects are being cancelled out, ruled out. Okay, hope you understood this part. Let's move to the third subset. See, if the electron's drift speed is small and the electron's charge is small, how can we still obtain large amount of current in a conductor? So the solution over here is given as simple. Why it's simple? Because electron number density is enormous, which is equals to 10 to the power 29 per meter cube. We need to understand this further. See, the drift velocity is in mm. The charge of electron is 1.6 into 10 to the power minus 19 coulombs. Similarly, the drift velocity comes in mm per second. Okay, this is very small. When both are multiplied, still it will give very less charge. Okay, but it is coming enormous because of the electron number density. Like if I am having one electron, it will produce something in this range, very small. But when I am having these many electrons, all these small electrons containing small charge, when added up, when summed up, will give us enormous amount of current. Okay, so like simply we have seen the drop makes the sea. Same comes here. Each and every electron contributes their amount of current, and the number of electrons in particular meter cube area, in 1 cubic area, is enormous, which gives us a enormous amount of charge. Like not the charge but enormous amount of current. Hope you understood. We'll move to the next, that is D sub part. When electrons drift in a metal from lower to higher potential, does it mean that all the free electrons of the metal are moving in the same direction? By no means. Drift velocity is superposed over large random velocities of electrons. Okay. Now you have to understand, in example number 1 we have read that drift velocity, if is in this direction, then E will be in the opposite direction. Drift velocity and the electric field applied are in the opposite direction. So what they are saying, if drift velocity is directed in this direction, does it mean that all electrons are moving in this direction? So we'll say no, it doesn't happen. These electrons show random motion, or some show motion in this direction, some in this direction. So they have this random motion. Okay, when this motion, when all these speeds are averaged, we get the drift velocity. It is a superposed velocity. Okay, it doesn't come from every single electron or one electron, but it is the composition of so many velocities, all the velocities random in this direction or in that direction, everyone. Then we are taking the average of it, which is giving us a single direction. Okay, now moving to the fifth subpart. Are the paths of electrons straight line between successive collision with the positive ions of the metal in the absence of electric field, in the presence of electric field? They are asking us whether these electrons travel in straight line path or they move zigzag before the in between the two successive collisions. Like we have to answer it both in the absence of electric field and in the presence of electric field. The solution is, in the presence of electric field, the paths are straight line. In the this should be, here should be the absence. In the absence of electric field, the paths are in general curved. Okay, how come that is happening? Like we are having this presence and absence. This is electric field. Okay, in this direction, this is electron. I'm having this electron. Now these electrons are randomly moving. As soon as this electric field is applied, these electrons align themselves in a straight line. Align themselves. But in the absence, these electrons do not have a like they are extremely random, some moving here, some moving there. There is no alignment in absence of E. So they move in curved pathways. So that's all for today's lecture. In the next lecture, we'll come with a new topic. Hope you are doing great and understanding these concepts well. Just go through it, practice this concept-based question. They are also equally important compared with the numericals. Have a good day. Bye bye.